Hey everybody, I hope that you had a great Easter weekend. I hope you got some solid R&R, rest and relaxation. This week in Honors Chemistry, we are going to work through Chapter 15 in your textbook. Okay, it's all about solutions. It's a pretty straightforward chapter. There's a few little calculations that we'll do, and you have a big owl set to practice. Sorry, I shouldn't have said a big owl set. You have an owl set that's totally manageable because the problems are not very hard, okay? It's just kind of one equation or one quantitative concept that we have to understand. And then the rest of this chapter, there's a lot of vocabulary, but the concepts themselves are pretty straightforward, okay? It's just the vocab that's going to be the biggest hurdle here for this chapter, okay? So this week we're going to get through chapter 15. Next week we're going to work through chapter 17. And then the week following that, we will have some sort of a test to cover chapters 15 and 17. Okay, so here we go. Let's just jump right in. We're going to start talking about solutions. Okay, so 15.1 is all about forming solutions and how do different substances form solutions or not form solutions. Okay, in order to talk about solutions, we need to understand solubility, but let's review some vocab, okay? We've seen this word before, this word solution, okay? We saw this way back in Unit 2, which was, like September, okay? We saw the word solution at the beginning of the school year when we were talking about types of matter. Wow, what a throwback! Remember when chemistry was just easy? It's still easy. For the most part, hopefully, okay. A solution is just it's another name for a homogeneous mixture or a homogeneous mixture, okay. And you'll remember that a homogeneous mixture is a mixture in which the components are uniformly intermingled, or everything's distributed evenly. Anywhere you sample in that mixture is going to be identical, okay. That's what we're focusing on in this entire chapter. It's all about solutions, okay. And there are two major parts to a solution. Oh, okay, these can be solid, liquid, or gas, okay? Not a big deal. Okay, the first part of a solution we call the solvent. Okay, the solvent is the part of a solution that is present in the largest amount. Okay, it's the biggest part of that mixture. It's a majority of that mixture is made up of the solvent. Okay, and the rest is made up of what we call the solute. Okay, the solute is the part or parts. You can have more than one solute present. Okay, but it's the part of the solution that's present in smaller amounts. Okay, and typically what happens is the solute is dissolved in the solvent. Okay, so think about putting, table salt into water. Okay, you know that table salt is going to dissolve in a big glass of water. Right, so there we would say water is our solvent, and table salt would be our solute. Okay, and we're going to deal mostly with what we call aqueous or aqueous solutions. Okay, these are solutions where the solvent is water. Okay, so these are mostly going to be liquid solutions. Your solvent is water. Okay, because that's really the most common thing that we work with in a chem lab, is situations where water is our solvent. Okay, so this is just some vocabulary that I'm going to be using that you need to be comfortable using. Okay, so the solvent and the solute are the two parts of a solution. Okay, solubility is the vocab word we use to talk about how well something dissolves in a given solvent. Okay, so solubility, the ability of something to dissolve in a certain solvent. Okay, and there's a general rule for determining if something will be soluble or insoluble in a given solvent, and that general rule we summarize by saying like dissolves like. Okay, so a solvent will dissolve solutes that are similar to itself. Okay, and so what we're going to see and we'll talk about today is that polar solvents, Okay, so this is where that molecule is polar. Remember, we kind of skipped molecular polarity. If you need to do a quick Google search to figure out if something is polar or not, you can. Okay. Yeah, I have no qualms about that. Okay, but a polar solvent is going to be a solvent where the molecules are polar. That will dissolve polar and ionic solutes. Okay, so these are going to be compounds that are polar, or ionic compounds will dissolve in a polar solvent. A non-polar solvent, again, you can do a quick Google search to see if it's non-polar, but I think you'll pick up on some of the patterns pretty quickly. Non-polar solvents can only dissolve non-polar solutes. So a solvent dissolves things that are like its. So let's look at an example of a solvent that we're going to see all the time in here, okay? And let's just kind of think about this concept of like dissolves like, okay? Will water dissolve polar and ionic solutes or non-polar solutes? Pause the video, see if you can think about it. What do you need to know about water in order to answer this question? Well, we need to know, is water polar or non-polar? Is it a polar solvent or a non-polar solvent? Well, I think most of you in here know, right, that water is a polar solvent. Okay, if you didn't know that, I trust that you can open a tab on your browser, type in, is water polar or non-polar? Okay, typically the first Google hit will be pretty okay with this kind of thing. So you could easily figure out that water is polar. Okay, if water is a polar substance or a polar solvent, it should dissolve polar and ionic solutes. Okay, so why is it that a polar solvent dissolves both polar and ionic solutes? Let's think of some examples of this. What is similar about table salt, sodium chloride, and sugar, C12H22O11, that allows them both to be soluble in water? Okay, I want you to think about that. Here we have table salt as an ionic compound, sugar is a polar compound. Why would they both dissolve in water? Well, think about it, right? Sodium chloride, ionic compounds. What happens that forms that ionic bond? Well, you have sodium losing an electron, chlorine gaining an electron, so you have a positive and a negative charge, cation and an anion, right? And they're attracted to each other, and that is that's caused by a separation of charge. You have some separation of charge going on. Same thing with sugar, right? You're going to have some carbon-oxygen, oxygen-hydrogen bonds. Okay, and when we did bond polarity, you know that oxygen is really electronegative. Okay, it's going to have a partial negative charge if it's bonded to a hydrogen or a carbon. Those two guys are going to have a partial positive charge. Okay, so oxygen is more electronegative. Again, just like with an ionic compound, we still have this idea of separation of charge, right? We have a partial positive, a partial negative. That's what is similar about ionic and polar compounds, is they both include on some level there's a separation of charge going on, right? And so if you have a polar solvent like water, polar dissolves, that polar solvent has separation of charge, and it should dissolve other things that also have a separation of charge. Okay, so next we need to talk about, like, how does this actually happen? Okay, how do things dissolve? So we're going to look at all of these examples, assuming that our solvent is polar, like water. Okay, again, most of what we're going to be dealing with in this class are aqueous solutions where water is your solvent. Okay, so let's first talk about ionic compounds and how do they dissolve. Okay, well, what happens if you take an ionic compound and you dissolve it in water, what it does is it splits apart into its cations and its anions, or it dissociates. It splits completely. So let's say you had sodium chloride. If you dissolve that in water, you can see you would have like solid table salt, solid sodium chloride. It's going to produce sodium ions dissolved in solution, and chloride ions dissolved in solution. And here's a nice little graphic to go along with that. You can see we have a little pile of solid sodium chloride. If you dump that into water, you can see we have the little particles representing the sodium and chloride ions completely separating from each other. Okay, so that's what happens when you dissolve an ionic compound. Let's talk about how that happens and why does that happen? Why does the water split apart the sodium and the chloride ions? Well, I'll tell you why. Okay, it's because the strong ionic forces holding that sodium chloride crystal together are overcome by the strong attractions between the ions and the polar water molecules. Okay, so that attractive force between your cation and your anion is overcome by all those water molecules, right? There's way more water molecules present. Okay, and those water molecules are attracted in a very specific way to those cations and those anions. And when that happens, they pull those ions apart. Okay, so here's a picture to show what that looks like. Okay, so if you look on the left there, we have our sodium chloride crystal. Okay, and then we have some water molecules floating around it. Okay, and look at the water molecule with the partial charges labeled. Okay, remember, oxygen is more electronegative, so we say that it has a partial negative charge. Hydrogen would have a partial positive charge. Okay, so when those water molecules with those partial charges kind of attack that salt crystal, what we see, if you look on the right side of this, okay, look at the upper right, there we have our chloride anion. Look at how those water molecules are arranged around it, right? It's those partially positive hydrogens that are attracted to that negatively charged anion, right? And then if you look at the bottom right, there we have our sodium cation, and now you can see it's that partially negatively charged oxygen part of the water molecule that's attracted to the cation there. So what happens is all these water molecules just engulf each of these cations or anions. Okay, and when that happens, it splits up that solid crystal structure and pulls off individual ions, and you get the crystal structure breaking down and dissolving. A very similar process happens with polar substances. Okay, so now let's think about, right, we said that a polar solvent will dissolve ionic and polar solutes. Okay, so let's talk about polar solutes. Okay, a polar substance, remember, has a partial positive and a partial negative region, just like polar solvents would. Okay, and this is kind of similar to the idea that we just saw with ionic compounds. You have water interfering with those partial positive and partial negative regions, and oftentimes this interference from the water is in the form of a hydrogen bond. Okay, so a lot of times the polar substances that get dissolved in water have that nitrogen, fluorine, or oxygen bonded to a hydrogen, and water is able to form hydrogen bonds. And when it forms those hydrogen bonds, again, it kind of gets in between the individual molecules of the polar substance, okay, and spreads it out and dissolves it in the water. So here's a kind of a picture to show what's happening. Right here we have in picture A, this is ethanol. Okay, ethanol is a polar substance because we have that polar bond between our oxygen and our hydrogen in that alcohol group. Okay, so we have that partial negative charge on that oxygen, that partial positive charge on that hydrogen. Okay, so if you add water to the situation, like we see in picture B, okay, we're going to have water molecules forming a hydrogen bond with the hydrogen from our alcohol group, okay, and our ethanol. And you can imagine if there were a bunch more waters here, you might have some bonding going on with the oxygen and the ethanol. Okay, but what happens basically is water gets in there, it interferes with the intermolecular forces within the polar substance or the polar solute, okay, and it ends up dissolving that polar solute. Okay, well, what about nonpolar substances? Well, water is a polar solvent. Okay, so it will not dissolve nonpolar things. Okay, and I want to talk a little bit about why. Okay, so if you have a nonpolar compound and you mix it with water, that nonpolar compound doesn't have any separation of charge. There's nothing for water to be attracted to, right? Remember, water still has that partial positive and partial negative region. If your nonpolar compound doesn't have any separation of charge, there's nothing for those water molecules to like kind of grab onto to help split up that nonpolar compound. There's no strong force that's going to allow water to get in there and break apart that nonpolar solute. So an example of a really big nonpolar compound, okay, this is a big carbohydrate, not carbohydrate, wow, hydrocarbon. Two different things, my friends. Wait till you get to organic chemistry in college. It's a vocab nightmare, okay? This is a hydrocarbon, okay? It's a big, long carbon chain with a bunch of hydrogens. Okay, this is a very common structure in like greasy things or oily things. Okay, they very often have these big chains of carbon. Okay, and so if you look at this molecule, there's no polarity there, right? A carbon-carbon bond is nonpolar, and we learned that a carbon-hydrogen bond is nonpolar. So there's no partial charges here that water could grab onto to rip these molecules apart. Okay, and so this is an example of why oil and water do not mix. Okay, because water is polar, oil tends to be made up of these long carbon chains. Okay, and so this is why oil does not mix with water, because water can't get in there and dissolve that oil. There's nothing for it to be attracted to, no way for it to split up that nonpolar compound. All right, so now that we've talked about how things dissolve, specifically in water, I want to talk now about what causes how quickly things will dissolve, okay? Or what factors affect the rate of solvation, okay? Solvation is the fancy sciencey word for basically dissolving, okay? It's the process of a solute dissolving into that solvent. So what are the factors that affect the rate or how quickly a solute will dissolve? Okay, we're going to talk about three of them, three major factors influencing how quickly something will dissolve, okay? We're going to talk about surface area, agitation, fancy word for stirring, okay, and temperature, okay? So surface area, we'll talk about this first. Solvation, or that process of a solid dissolving, that happens at the surface of a solid particle, right? Because it's that outer surface of your particle that is exposed to your solvent, okay? So the more surface area that's exposed, the faster the rate of solvation will be. Guys, that just makes sense, right? The more area available for the solvent to get in there and start breaking apart your solid solute, okay, it's going to dissolve faster. Duh, okay? I'm not trying to make this hard. Like, some of these things are like, okay, yeah, that makes total common sense, okay? Well, what if you have a solid and, you know, you want it to dissolve faster? How can you increase the surface area? Get a glass stir rod and start squishing it down in there, okay? You can increase the surface area of a solid chunk by crushing it into smaller pieces. Okay, if you have a bunch of small pieces, you're exposing more of that solid surface area, and you'll expose more of it to the solvent, and it will dissolve faster. Okay, and if you don't believe me, here's a diagram to show that, you know, you could have the same volume of substance, or the same like mass of substance. Okay, but you can see in the cubes on the right, it's been squished into 8 pieces, and all that inner surface that was not exposed in the bigger block now is exposed in the 8 smaller blocks. Okay, and you have increased the surface area. Okay, so if you increase your surface area via crushing, it will dissolve faster. Okay, and you've probably all experienced this in real life at some point or another when you're trying to dissolve, I don't know, like hot chocolate or something, you know how sometimes you'll have like that wad of the chocolate powder stuff like sticks together, and you can like kind of like pop it, and then you see all that powder on the inside that hadn't been exposed to the water yet. All of a sudden now it gets exposed and it dissolves faster, and your hot cocoa is yummier. Now I want hot cocoa. Okay, the next thing we're going to talk about is agitation. Again, if you've ever made hot cocoa from powdered mix, you totally know how to do this, okay? We're just going to talk about why it makes sense at the particulate level, okay? So again, agitation is just a fancy word for stirring, okay? What happens to a particle when you stir it, okay, is that abrasion on the surface, it's removing particles that have already been exposed to the solvent. It's kind of brushing them out of the way and exposing fresh surface. And it's saying, here you go, solvent. Here's some fresh surface for you to dissolve at. And it increases the solvation rate, okay? You guys know this. If you make hot cocoa, I mean, if you just dump in the powder and let it sit, I think eventually it would dissolve, okay? But you all know, you got to kind of stir it to get it to dissolve in the amount of time where the hot cocoa would still be hot when you drink it, okay? Otherwise, it's just like, you know, cold hot cocoa is like watery chocolate milk, and ain't nobody want to be drinking that, okay? Stir your hot cocoa so you can drink it while it's still hot. Capiche? Okay, this gets us to the last factor affecting how quickly something will dissolve, and that is the factor of temperature, okay? Here's why higher temperatures make things dissolve faster. It's because at a higher temperature, those molecules within your solvent are moving more rapidly, right? If you heat up water, there's more kinetic energy, and those particles, they're moving faster, and so they're able to get in there and break up the solute more quickly just because they're colliding with the surface of that solute at a higher amount of energy, or they're hitting it harder, okay? Something else that happens with an increased temperature is you can actually dissolve more stuff in your solvent, okay? If you increase the temperature of water, you can actually dissolve more solid in there. And we'll get to that a little bit more in a second, okay? That's for solids. The opposite is true for gases, okay? Gases are less and less soluble in a liquid at a higher temperature, okay? So here are kind of some graphs to summarize that. I mean, if you guys just think about what's going on with kinetic energy, this should make pretty good sense, okay? So solids experience increasing solubility at higher temperatures. Gases experience decreasing solubility, okay? Look at the temperature solubility graph for gases there on the right, okay? Think about a can of soda pop, okay? When it's fresh out of the fridge, it's nice and fizzy, right? It's nice and it's got that nice soda pop fizziness to it, okay? That's because it's cold. At a lower temperature, you can see gases are more soluble. That carbon dioxide in your pop it stays dissolved in that cold liquid in the soda a lot better, okay? As your soda pop sits there, let's say you set it down and forget about it, or you let it sit and it starts to get warm, okay, as that temperature increases, that carbon dioxide gas becomes less soluble in that liquid. Okay, so that means some of that gas is going to escape up to the surface, okay, and your pop is going to go flat. It's going to lose that fizziness, okay? All right, so now that we've talked about how quickly something dissolves, we just got to learn a little bit more vocab, to better understand some of the features of solutions, okay? So we're going to look at qualitative descriptions of solutions in this, and then tomorrow we'll look at quantitative, okay? So qualitatively, we can talk about how close a solution is to reaching its limit, okay? There is a limit to how much stuff can be dissolved in a given amount of solvent, okay? And so we can talk about a solution relative to this limit point, okay? And here's some of the vocab we can use. We can say a solution is unsaturated. Okay, it's unsaturated when it has not yet reached that maximum amount of solute that it can dissolve. Okay, if you have an unsaturated solution and you add more solute to it, it will still dissolve because it hasn't reached its maximum limit yet. Okay, unsaturated. A saturated solution is one that is at that limit. Okay, it's reached how much solute it can dissolve. It's kind of maxed out. Okay, if you added more solute to a saturated solution, it would not dissolve. Okay, if it's a solid, it's just going to kind of trickle down and sink down to the bottom of the container because there's no more room for it to dissolve in that solvent because that solvent is saturated. Okay, so here are some visuals. You can see an unsaturated solution. Everything is dissolved, and in fact, it can dissolve even more stuff. Okay, then we have a saturated solution there. Don't worry about the words. But you can see there's a pile of stuff down at the bottom, and that's because whoever did this kept adding sodium chloride to the beaker after it had reached its limit point. So that solid sodium chloride had nowhere to dissolve because the solution was full. It was saturated. Okay, and then sometimes we have a very special, very rare situation that can happen. It doesn't tend to happen naturally. It happens in the lab, and that's about it. But it is possible to have a solution be what we call supersaturated. Okay, and a supersaturated solution is one where you increase the temperature of your solvent. Okay, so remember we said at a higher temperature, solubility increases for solids, so you can dissolve more solid at a higher temperature. Okay, so if you raise the temperature of a solution and you saturate it, okay, at that elevated temperature, okay, you fill it up to its maximum amount of solute that it can hold, and then you just let it sit there. You let it sit there and you let it cool down. Okay, sometimes you can get all of that solid to stay dissolved even as the temperature decreases and the solubility of that solute would naturally decrease. Okay, but here's the problem with supersaturated solutions. They are super unstable. Okay, they don't last very long. That's why they really only happen in a lab setting. Okay, and here's why they're so unstable. If you just tap the beaker or you add one more crystal of your solute, everything else precipitates back out. Okay, it all resolidifies. There's a really cool video. Okay, I would click on this link, watch this happen. It's really beautiful. It's kind of a cool demo. Maybe some of your teachers did it in elementary school for you. It's just really beautiful to watch because you can see the nice crystal structure of that solid reforming back out of solution. Okay, so unsaturated, saturated, supersaturated. That's talking about our solution in terms of where is it relative to that limit or that maximum amount of stuff that it can hold. Okay, the other qualitative language we can use to talk about a solution is to talk about it in terms of, relatively speaking, how much stuff is dissolved. Okay, so it's not really related to that limit or that full or that maximum point. Okay, it's more comparing it to a different solution. Okay, so these next two terms we're going to look at, you tend to have to be comparing two different things to use them. Okay, they're relative to one another. Okay, so the first thing we could say is that a solution is dilute. Okay, something that is dilute means that a relatively small amount of solute is dissolved in solution. Okay, and that is opposed to a solution being concentrated. Okay, if a solution is concentrated, that means it's got a relatively large amount of stuff dissolved in solution. Okay, so here we have two beakers. We have solution A and solution B, and you can see relative to each other, solution A has fewer particles dissolved than solution B. Okay, and so here we would say solution A is more dilute than solution B. Solution B is more concentrated than solution A. Okay, it's possible we could have another solution that only has, you know, 2 molecules dissolved or whatever, 2 little particles in there. Then we would say that one is dilute relative to solution A. We would say A is more concentrated than that one. So you can see it's kind of more of a spectrum, and you need to have specific things that you're comparing if you want to use these words of dilute and concentrated. Okay, whereas unsaturated, saturated, and supersaturated, that's based on the properties of the solvent and the solute, and that's like a very specific point where that would reach saturation. Dilute and concentrated are more relatively speaking, okay? And just a quick note, and we'll talk more about this tomorrow, it's important that you consider both the amount of solvent and the amount of solute present, okay, when you're using these ideas of dilute and concentrated. So as an example, here, look at these 2 beakers here on the bottom. Here we have solution X. It has 2 particles dissolved in 1 liter. Okay, solution Y has 4 particles dissolved in 2 liters. Okay, it turns out these are equally composed, okay? Neither one is more dilute or concentrated than the other, and that's because that ratio of number of particles to volume is constant. And we are going to talk a ton more about that tomorrow. I'm going to shut up because this video is getting crazy long, okay? Thanks for your patience, y'all. Just get down these notes. Again, today was mostly conceptual and a lot of vocab, so that's kind of why this lecture video went on for 5 million years. Sorry.